Let's explore the derivative of the absolute value function. The derivative of the absolute value of x, with respect to x, is given by x divided by the absolute value of x. This expression can also be written in piecewise form. It equals -1 whenever x is less than 0, and +1 whenever x is greater than 0. In fact, this piecewise definition is exactly the signum function. So we can write the derivative of the absolute value of x as the signum of x, valid for every x not equal to 0. The absolute value function is differentiable everywhere except at the origin. Its derivative behaves like a step function. That step function is precisely the sine function, sgn of x. But right at x equals 0, the derivative does not exist. We can express this more explicitly as a three-branch piecewise function, -1 for x less than 0, undefined at x equals 0, and 1 for x greater than 0. Now let's prove this result rigorously, starting with the chain rule method. By definition, the absolute value of x can be rewritten as the square root of x squared. We differentiate both sides using the chain rule. Applying the power rule to the outer square root, and the chain rule to the inner x squared term. The derivative of x squared is 2x, so we substitute that in. Simplifying the constants in the numerator and denominator. And since the square root of x squared is exactly the absolute value of x, we arrive at our final result. This completes our derivation using the chain rule. Equivalently, using the sine function notation, this is the sine of x, for all x not equal to 0. Now let's investigate what happens exactly at x equals 0, using the limit definition of the derivative. Recall that the derivative at a point is the limit of the slope of the secant line as the interval shrinks to 0. We set up the difference quotient at x equals 0, using f of x equals the absolute value of x. Substituting, this simplifies to the limit of the absolute value of h, divided by h, as h approaches 0. Let's first consider the right-hand derivative, where h approaches 0 from positive values. Here, the absolute value of h is simply h, so the ratio simplifies to 1. Now consider the left-hand derivative, where h approaches 0 from negative values. Here the absolute value of h equals -h, so the ratio simplifies to -1. Since the left-hand derivative and right-hand derivative do not agree, the two-sided limit does not exist. This means the absolute value function is not differentiable at x equals 0. Let's visualize this geometrically to build intuition for why the derivative fails to exist at the corner. Remember, the derivative at a point is the slope of the tangent line to the curve at that point. Here is the graph of y equals the absolute value of x. Watch this point as it slides along the curve toward the origin from the left. Notice that the tangent line maintains a constant slope of -1. But as soon as we approach from the right side, the tangent line slope jumps instantly to +1. At the corner itself, two different tangent lines meet, one with slope -1 and one with slope +1. Since these slopes disagree, there is no single well-defined tangent line at x equals 0, confirming that the function is not differentiable there.